Thank you. Good morning, everyone. Thank you again for joining our weekly seminar. We have the upcoming events shared on the screen. Please plan to join us for the future events. Particularly, the next meeting is in person, and we'd appreciate if you can attend the meeting in person. Today, we are privileged to have Professor Amit Sheth from University of South Carolina. Professor Sheth is the founding director of the University AI Institute, NCR chair, and professor of computer science and engineering at the University of South Carolina. He's a fellow of IEEE, AAAI, AAAS, and ACM, and he has won many awards, including IEEE CS Wallace McDowell Award and IEEE TCSVC Research Innovation Award. And he has done influential research in artificial intelligence. And today we are privileged to have his talk from NLP to NLU, why we need varied, comprehensive, and stratified knowledge, and how to use it for neuro-symbolic AI, which is one of the research topics in AI. With that being said, I ask Sheth to start.
Thank you very much, Mohammed. Thank you for giving me this opportunity. It so happens that my university used to be called USC of the East. And then they changed the name, the abbreviation from USC to U of SC, U of SC. And then just this year again, we got a new president in last year rather. And the board and decided that we're going to go back to USC. So now we are again back to two USCs. I started founded the AI Institute of South Carolina 3.5 years ago. Today I'll be talking about, this topic of, bringing the next generation of AI system called Neuro-symbolic AI system, where particularly a class of those systems where knowledge plays a critical role for binding or for the capability that it has. I had given this talk just recently at a workshop on knowledge NLP at AAAI. So this is more or less the same talk. So the AI Institute, covers the topics, key topics that we are working on are, at the core areas of AI that you can see, in the middle, and we have very large interdisciplinary and translational AI portfolio. So we have many of our projects essentially are more scaled up projects. So they involve real world problems and collaborators from each of those different disciplines that you see here. Their data, their subjects, maybe patients in the case of medical or other, healthcare discipline. And we do algorithmic innovations and technology and tools, but we test it also out fully. This general philosophy has helped me also kind of take the technology to the real world. I've founded or co-founded 4 companies, including Tali, that had pioneered the knowledge graph enhanced semantic search in year 2000. That is when the patent was also awarded, 2001. And there's the same general philosophy you saw in the Google search in 2012 and 13. And the last company that I did is combining emotion and AI. I know that AIISC also does a lot of work I want to just start with picking one area where there is a potential synergy. There is a group at AIISC. You guys have developed a tool and given tutorials on, basically managing, knowledge graphs aspects of it. So it's centered around a lot of graph-related capabilities. We have just recently completed development of a rather comprehensive platform that supports from really development of large knowledge graph from the scratch, and so it does the functions you see on the screen, and we are able to then develop large scale knowledge graphs such as the one we have done, and it is still work in progress for pharma knowledge graph. So diverse unstructured to structured knowledge sources, and bringing knowledge from many of those sources into something cohesive. Okay, well, that's enough about the synergy and possible interest. So coming to the topic of the talk, these are the things that I'm going to discuss here. And I'm going to go through evolution in the role knowledge has developed in developing this neuro-symbolic AI system. So we call this knowledge infused neuro-symbolic AI. And then there is a new version of that that is evolving, which I will touch upon at the end of my talk. It's hard to escape the impact of generative AI. But we find a lot of challenges with generative AI. It is amazing technology. It solves 80% of the problems very well. It does some unique things that we could not do a while ago. It is very much easier to use for and has gotten the attention of common people and people from wide variety of disciplines and activities. And yet, there will be quite a bit of challenge, particularly the distributional semantics just does not have the understanding, and it just does not have WorldModel semantics, as I would call it. So the factual information that we all know and use, that's something it does not have. It can potentially allude to that. It can talk about emergent capabilities, but it's not the ingrained, true capabilities. So, the question I asked there is, do WorldModel semantics arise as an emergent capability of distributed semantics at scale? And really not directly, not specifically, not adequately. So understanding what you have in mind. Now, these things are complementary. A while ago, I wrote a paper called Semantics for the Semantic Web, but more importantly, the implicit, the formal, and the powerful. So the implicit, semantics that you get from your distributed semantics, the formal, the one that you can get from the WorldModel, from the knowledge graph, and then the powerful ways, different ways you combine those knowledge in, with the inclusion of probabilistic representation and more. It just does not have certain core understanding. You may ask the question about Obama. So Obama just won 2032 election, and it really doesn't understand that. It will give you something, and it doesn't say that, look, 2032 has not happened, and that's the end of it. So that understanding of the real world is just not there. You ask it to you have problem with this low probability, so and also lack of common sense. So what was the color of the white horse of Napoleon? And well, the color is right there, and yet it does not understand that concept of color, and that it is in the text and such. You would ask this other question. Mike's mom had 4 kids, 3 of them XYZ, and what is the name of 4th? Well, doesn't understand the concept of that there's missing information here. It doesn't obviously rule out that Mike is not a pet, and so on and so forth. So it does not have common sense, and the probability does not help. A lot of concepts have low probability in its in what it has created from the data. It does not have the ability to make human-like assumptions about missing information. So, you interact with it, you say it is Mike's mom, so Mike is the answer. Again, it does not understand those things. It was asked, what is the, about me, and it just made up. So, hallucination, hallucinate is something that we all are aware of, but here it makes up a name of institution, artificial integrated intelligence system center. Well, there is no such thing. And when you go back to ask what institute he belongs to, he's not aware. So really just did not understand anything really. So there are quite significant challenges. Here are there is a partial list of the challenges that we see with this discipline semantics. And I'll be talking about 3 or 4 of them today. So this here we portray on the x-axis what is, what I would call language processing versus language understanding. And then on the y-axis, understanding at just one of the many aspects, one of the many dimensions, what you might call developer interoperability versus user explainability. And in the deep neural network, yeah, you can provide some help to interpret how the deep neural network works to a machine learning engineer. But if you have to explain to the end user how you got to what the answer is, what the recommendation is, what the prediction is, then that is something you don't have. Through the embedding, you can reach partway, but not fully, because when you bring the knowledge down to the data level, and when you create a vector from the knowledge, you lose a lot of semantics, quite a bit of semantics, in fact. So that is an interest or well understood stopgap solution, but that's not really a very good solution in the long term. So here you can see very partial portrayal of the choices that we have against us, from deep neural network to embedding in deep neural network to knowledge infused neural symbolic AI, which I will talk about today. Why is that the issue? This is it's very strange, but let me go here and see what happens. Let me get past the slide.
While you're bringing up the slides, I wanted to say a correction. The next AI seminar with Raymond Mooney will be held on Wednesday, May 15th at or March 5th. 15th, I think, at 11 a.m., not on Friday, as it is on this slide. Sorry about the interruption.
Okay, going back to our talk. There's an interesting thing that ChatGPT did, this InstructGPT, where you incorporate human in the process. But that I see a lot of challenge with that approach. First of all, you got some 40 people involved in in this process. That is really not adequate to really capture all the knowledge that is out there and that you need to solve problems. Then what happens is that you reduce the work that they are doing and the choices they are making into a label. And a label is not a adequate capture of the semantics of what choices are being made or what knowledge is applicable in solving that problem. So, this ability or this feature of hallucinations is not something that is going to be solved just by making these models larger and or incorporate this instruction-based training. It does have some interesting, it does present interesting advance, but it's not really going to, capture really give you a full solution. So richness of human knowledge simply cannot be captured into a mere label. And there are, if you think about the knowledge, there are concrete things that are easily available, such as the one thing, the knowledge you're seeing on the left-hand side, the roles, the relationships, and that kind of representation can give you a true understanding. The other thing is that in the activities that humans do, particularly for natural language understanding, a lot of different knowledge get applied. You have, right now, as you listen to me, you're applying, lexical knowledge. You know how to parse a sentence. You're applying linguistic knowledge. You're applying common sense knowledge. And we have representations for all of them where massive amount of human effort has gone in to create those knowledge graphs. You have general purpose and broad-based knowledge, Wikipedia, Wikidata, and you have domain-specific knowledge like UMLS or DSM-5. So all these knowledge get applied, and there is a role for all of them. And practically, you need all of these to really understand. And this is something that generative AI models simply don't have, right? And to expect that all of these knowledge would be somehow mimicked in this distributional semantics with probabilities or on the words, that's just not going to happen. There are the knowledge graphs give you this explicit model for recency and common sense. They supply missing knowledge of entities in relationship. They, they have world as a concept rather than world as probabilities, and that they can support user level explanation and safety constraints. So let us look at knowledge infused neuro-symbolic AI using graphs in neural network pipeline. A few years ago, we talked about a variety of architectural solutions. One is called shallow infusion. And generally here you are taking the knowledge and creating vector and incorporating that at the input level. Then comes the semi-deep infusion, where you can bring that knowledge somewhere in the pipeline and also at the input level, and you can modulate or deal with the parameters involved. And then a deep infusion model where you can actually bring in the knowledge at different levels, input, parameters, output, and you can apply the knowledge, different knowledge at the different level of abstractions. It so happens that AI system has become incredibly good in the activities involving kind of low level of intelligence, as I may say, like classification, recommendation, ranking kind of thing. But it does not do well at all with high level of activities such as abstractions, analogies, and things of that nature. So there's a lot more to be done there. And I described to you this, abstraction, this, a set of knowledge, the tiers of knowledge that I described. Those are the different level of abstraction that you need to serve and support. This is strange. So with regards to then use of all these choices you have, distributed semantics, shallow infusion, semi-deep, and deep infusion, let me just kind of give you a very high level perspective for hallucinations, that distributed semantics performs very unsatisfactory. With shallow semantics you can get by, but really not solve the problem. You do a little bit better with the semi-deep infusion, and then with the deeper infusion, you can broadly solve the problem. So now to think about this neuro-symbolic architecture with knowledge as a key component, here is a generic architecture that I can present. You have both data and knowledge rather than just data. That's of course the key. You have the primary, something like transformer. You have something, feature abstraction layer, which computes all these probabilities. Then you have the knowledge and the ability to reason, which is C. You have neural reasoning, perhaps supported by feed-forward network. And then you have the workflow and process guided reasoning. You might have to take, you might have to go through a set of steps, one after another, before you can arrive at a decision. So for example, in clinical situation, symptoms, and then, you run the labs, and then you, come with the diagnosis, and then you do the, then you do the remedy, or treatment. Now there is that set of process that you need to do, which is specified by, let's say, clinical practice guideline. And you just simply can't jump to a solution. It's not a one-shot solution. And so you need to bring the process of decision-making into the, processing pipeline. And that is what item number E describes. I don't want to take time to debug that, so we are just going by. I thought last time I checked, there was no such problem. So before the transformers, here is an attempt that here is the work that we had done. We had this is an example of shallow infusion, where what you see is that you have the your embedding, and you take your data and create you use a deep learning technique, but then you have knowledge processing and understanding. So here you have for example, OCD or suicidality related diagnosis. So these are variety of mental health conditions you see on the top in the box C, right? And on the other hand, you see so with regards to those medical conditions for mental health, you are able to identify various concepts that occur in the text. Correspondingly, you are able to create a so on the right hand side, you see the green, which is the your normal embedding embedding, and on right hand side you see the knowledge enabled layer you have created that captures the semantics that comes from the appropriate mental health related knowledge. And with that knowledge, so there are these DSM-5 categories and the lexicon. You are combining that knowledge with the the statistical processing, and hence coming up with the knowledge informed processing, which then gives you far better results. You see on the top right, using different choices and different knowledge and constraints, you could substantially, in this graph, we show the error rate. So starting with some high error rate of something like 30%, you are able to get it down to 2.5%. So the knowledge can have substantial impact on what we can, the outcome. Now, since the transformer, architecture came about, there have been a number of approaches to incorporate knowledge. So one of them is called K-adapter, and here on the right you see the transformer layer. In the box B, but on the box C you see an embedding that is created from knowledge, and the only thing is that here the embedding size is not the same as the one that is for the transformer layer, so you have to use the projection. But in the process, you do lose quite a bit of semantics, or quite a bit of what is captured in the knowledge. There is an ability for this architecture to have multiple adapters and hence incorporate multiple knowledge. But the core limitation of neural network or statistical processing still remains. So, for example, you see the question is that of native language for Manmuti, and the answer is Malayalam. But if you see the answer, K-adapter, it says Malayalam, Tamil, Hindi, and various other languages, right? So clearly there is not enough of a true understanding. The answer is just Malayalam. There is no, a relationship of Tamil or Mandarin or English in the context of native language with Manmuti, right? So clearly there is no understanding. Yeah, it got the probabilities right here and really highlighted the first item, but you never know whether the second item is relevant or not, or how relevant it is from the real world context. So that is a substantial challenge that we face. Let us look at another approach. This is called Kala, and here they you see the pay attention to the box C, and here the knowledge of something that is an instance of an entity, or that that New York is in country USA. That knowledge is lost in the embedding process. You can use the weights for the different relationship of country and instance of, but that loses the real knowledge there is in terms of what you see there as a something. New York is an instance of a city and other thing. In the end, what you can do here, if you see the bottom right, is that it is able to kind of without the knowledge infusion, you can see that retinal and genes are far apart, and it is simply able to bring them together. But nevertheless, there is no true understanding, and that is just a very unsatisfactory kind of results, where you somehow are able to bring them together. What is the real meaning? How can you apply to the real decision making using this kind of thing. That is just not clear. So then comes this other approach that we developed. In here we call TDLR. What we are doing is to create a mask. So you see here in the C again box, you're creating a mask, and you are applying over your self-attention matrix the outcome of your transformer based system, and using that mask which retains the knowledge, where you are able to incorporate knowledge into the deep learning system, into the statistical processing or neural network system, without going the embedding route that loses the semantics. So the end result is that it understands, you see on the bottom right, that a Great War is synonymous with World War I, or the First World War is synonymous with World War I, and that so that is a far more clearer understanding of the real world compared to what kind of approximations like ranking of the terms that you can come up with, or better clustering you can come up with, right? So there is a lot more clear, deeper semantic understanding retained in this process. And there are a number of artifacts, a number of things here. This you can see that you can work with different size of the model, and this TDLR base competes very well with the large model of the of the SOTA. And the bottom one shows that even when you use a smaller chunk of the data, then also you can have fairly good performance. So both in the model size and in the data context, the use of knowledge improves upon the alternatives. So let us look at now a couple of other things. Here is our generic architecture of knowledge infused learning as we are pursuing now. And there on the top left is the neural network. And now, until now, we've been focusing on taking the knowledge and somehow making part of the neural network system. What if we are able to elicitate knowledge from neural networks and then combine that with the symbolic knowledge? If you can do that, then you can more easily apply the reasoning. You can do planning, you can do inference-based reasoning, and you can apply the variety of knowledge such as process knowledge that I earlier discussed. And you can interact with the system much better, because we know that the neural network systems are black box. They don't give you the insight, but humans understand knowledge graphs. Humans can view the knowledge graph and really have far clear understanding, because you have entities, your relationships, and other things to represent the knowledge. So and you can incorporate different pieces of knowledge as it is in the middle here, and that would be that sounds like an attractive option, and which we are pursuing. Let us look at an important benefit of doing so. So here you are seeing a text. In this case, it is from Reddit, and you can make use of neural network for entity detection and finding the appropriate various phrases. But then by connecting them with the knowledge, you can see on the left hand side the knowledge graph, where you have taxonomic relationship. You know that feeling hopeless is level of mood is or that you can see that high risk bisexual behavior is a type of health related behavior finding. So you can really add the semantics that knowledge graphs have, and even if the concepts that are in the text are at different level of abstraction, through the use of knowledge, you can consider the alternatives going up the hierarchy if needed, and then you can start to connect that to the appropriate understanding that humans would have. So a mental health professional who has used DSM-5 or follows DSM-5 would see this definition on the top right. And, the definitions say that, in this medical condition, you see this, but not that. And you be able to use that definition and see how that definition is followed. And even not only that, but you could even construct you can do natural language generation and construct a language, a natural language explanation as to why you think this text, really belongs to this concept of OCD. So you can provide the explanation in the form that end user like patient or clinician can use. And here, let's say that you're talking about detection or concepts within suicide. Then there is a well-known guideline called CSSRS, Columbia, and then suicide scale, and they have given us, or they discuss how you essentially decide whether it is indication, ideation, or behavior and attempt, right? And when you come across a text like this, you are able to follow that process, that flowchart, that decision-making process in coming to the decision-making. So here in the case of this text, you found variety of components, and you are able to ask, does the person wish to be dead? Is there a non-specific active suicidal thought? Is there a support for active suicidal ideation with some intent to act? Then you are going to label it as appropriate, this kind of thing. This kind of activity is now possible that otherwise would not be possible without the use of knowledge. So here, a very important thing you see on the top, top right in that graph is that the results of classification from language model versus the use of process knowledge and showing how you came to the result. And when we showed it to the clinicians and those who practice this particular neuro activity in suicide idea detection, then they found this process knowledge supported alternative far better, right? So hopefully that can lead to much better and see, given that there is a clarity as to why you how you are able to follow CSSRS and why you are able to come to that particular conclusion, that is very critical for them to really accept your solution or not. Now, the other important thing that you can do with this kind of use of knowledge is that you can make the system safe. So we have developed a knowledge, a mental health virtual assistant or chatbot. And there are some very well-known examples of big failures of language models. So, for example, a well-reported case is that of a person interacting with the chatbot and a person asks, "Should I commit suicide?" And then chatbot says, "Yeah, you probably should." Right? So that is very, very unsafe. And this is what would make use of language models, at least today's language models, not appropriate for many critical applications. And the other interesting thing is, important challenge is that you have to be mindful about who are you interacting with. So in this case, you see there is an interaction, and the language model came up with the natural language response or question: do you feel irritated or self-destructive? And now if you ask a mental health professional, they would say that is not how it should be phrased, and this could create a challenge. So we show in our work that you can really construct your conversation that is much safer, and avoid going on in the areas that are unsafe, that may be they may have emotionally negative connotation, that go along the concepts that are not appropriate. As another, as an example, we decided that we should first develop and test our chatbot for milder mental health condition, such as relatively mild, such as anxiety and depression. And we should make sure that our chatbot does not engage with the patient on things like schizophrenia or suicide. So putting the guardrail, ensuring that there is a whole scope of mental health, and that this is your sandbox that you can play in, but you should not go into these other areas. That kind of thing is also quite possible, because you able to talk, constrain the system behavior and modulate it and guide it based on the domain knowledge and or guidance by the experts in the domain, right? So that is another very important things. So besides creating medically valid and safe questions, also the questions in right sequence. For example, the process knowledge can say that you want to first find out this, and based on that you want to ask these questions, not in some arbitrary order. So that is another important thing that you could do with this kind of language. Sorry, this kind of approach. So then that brings us to my slide, to my virtually the last slide, where I like to summarize what we discussed today and open up for questions. So if the system were to give user level explanation, you'll need to incorporate a conceptual model, vocabularies, knowledge graph that are used by the user, and specifically that user. So you can't, it's not sufficient that you train the model on some very large corpus, but not relevant to this particular user, or there may be two different way or style or method of dealing with the situation, and this particular group wants to follow one or the other. Well, you need to be able to constrain that. Also, so the purely data-driven system can at best give explanation that machine learning engineers or developers can use, but not what the users can use. Knowledge is second point. Knowledge is multifaceted. I made a case that you need to have diverse knowledge to support different levels of abstraction for NLU. So yes, it's certainly there is some knowledge needed for linguistic or lexical aspects of it, but there's a different knowledge needed for common sense, and yet another for incorporating medical knowledge. And there is no one single large knowledge that you can use either. There is a big importance of abstraction. There are a number of thinkers in the AI that have understood the importance of abstraction and analogy. Melanie Michel does talk about it, and there are a number of others who have recently talked about the next challenge to the AI, which is in the abstraction. And we think that we have an initial kind of approach to start supporting that, because in the deep infusion techniques that we have developed, we are able to incorporate knowledge and do so selectively at different points and parts in the neural network architecture, at input for parameter and attention metrics, for output at the end. And that kind of thing, flexibility is necessary to create a system that somehow is closer to the way humans make decisions. And then you have the challenge about whether to bring knowledge to the data level, do the embedding, and or bring the data to the knowledge level, learn from the data and align with the knowledge. So I've been pushing my team to really figure out a good way of doing the latter, and we have some initial success in doing that also. So what I call is less demanding intellectual activities like classification, prediction, recommendation. The former can often be sufficient, but for more demanding intellectual activities like decision making, taking actions with explanation, I pretty much believe that the latter is necessary. With that, obligatory, support for our research, primarily from NSF, but also, a couple of awards from that, but also some other sources. And then there are a lot of sources where there's a lot more you can learn about. And this is, my team, both the institute level and my core, immediate advisees and mentee, and also the students who particularly help in doing this work. With that, questions?
Thank you so much for your interesting talk. If you have any questions, please use the chat box, and I'll try to read out your question. So I have a question. It looked like to me that the knowledge graphs that you are, or maybe you can correct me, the knowledge graphs that you are talking about are static knowledge graphs. I wanted to know how difficult it is to work with temporal knowledge graphs where the edges are changing over the time. I guess that might be something common in clinical data, and how different those knowledge graphs are with the static knowledge graphs.
Yeah, getting the knowledge graphs, incorporated with the neural networks goes some way, but we earlier talked about the large language models you train on a huge corpus. It's a massive effort. GPT 3.5 was trained in September or November 2021. So it simply would not have any ability to deal with some recent news or new knowledge. Now there are several options that you can consider. First of all, representation of time, and more broadly provenance in the knowledge graph itself. So one of my PhD students' dissertation is on contextual knowledge graph, and she has done, her whole dissertation was about representation of the context, including time, in the knowledge graph. So we do need to, you do need to make the knowledge graphs, the representation richer to be able to support time and other things, including the source of information, other things that will be necessary. And the second part is being able to incrementally update the knowledge graph. That part we are able to do now. In fact, that part we did it long time ago. When I did my second company, Tali, we used to run knowledge extractors at regular time interval or predetermined time interval. They'll go to the knowledge source and pick up the new knowledge and incorporate the knowledge graph. For example, we had a part of the knowledge graph that dealt with markets. And within the markets, you have NASDAQ. NASDAQ has stock listed and delisted regularly. So, a stock that was listed and part of NASDAQ component may no longer be there after some time. So you need to have that recent knowledge. So the knowledge extractor would run, at period day, including daily, and pick up the new knowledge, delta knowledge, and then incorporate that delta knowledge in the knowledge graph. So those are the dynamic knowledge graph. There is some very limited work. My group started work on that area, and we had very preliminary work in that area, and more, but much more needs to do. So dynamic knowledge graph and its incorporation into the system. Now this whole system is such that incorporation of dynamic knowledge graph in the neuro-symbolic AI is, I don't think, a big problem. But creating and maintaining knowledge graph with the knowledge changing around us, that is still something that can use more work. We appreciate the issue. We have done some work in that, but there are many issues. For example, scalability of representation for contextual knowledge graph. There the triple subject predicate object won't do. You need to capture time, or you need to capture other aspects of provenance. Well, that would require more components, and as you do that, your storage, your computation, your querying, all of those get affected. So there are engineering issues, performance issues, storage issues, even the query language issues that you have to address. We have done some work in that area, but I think that line of work requires needs to be taken into much more well-engineered system that we don't have today.
Thank you. A somewhat relevant question: how to incorporate knowledge graph dynamically during conversational AI and chain of a QA model?
Yeah, so that is reasonably doable. If you go to wiki.AIISC.ai, here is a mental health projects, and we have a system called Alleviate for mental health, and you can play this. This was a demo given at, also presented at AAAI just about a month ago. Here the knowledge graph is being consulted, and you can restart the chatbot and ask it to use the new knowledge, and you can do that as often as you want, like for every patient session, and you can use new knowledge. So that part architecturally is quite doable.
The final question: have you considered recent works in quantum natural language processing, which takes this problem of true understanding from a different perspective? It incorporates meanings at the word level, similar to your argument of knowledge of world need to be learned bottom up from meanings and not from probabilities and contexts, and then combines the information flow between words using grammar to create sentence rich in meaning. I think a combined model where the meaning is provided by Q and NLP and then propagated by knowledge graphs might be a good solution. Rather long question.
Okay, well, this is frankly, this is new to me. I am not aware of quantum natural language processing. I will certainly be interested in looking it up myself later on. But I do want to point out the important thing. Take an example. In one system that we developed, this was a system where we worked on explaining why traffic slows down, and we did that work on Bay Area. So we collected 1 year worth of road network data, so very large data set, and corresponding data from Twitter coming from that region over that period of time. And whenever traffic slows down, for example, first of all, traffic slowdown is contextual in the sense that there is an average speed of 30 miles per hour on some day at some time, which is reasonable and normal, and some other time the normal speed may be 50. And when there is supposed to be normal 50, and at that time, in that hour, your speed is 30, then you say traffic is slowed. So that itself, finding anomaly in the traffic, information by hour over 7 days of the week, where traffic flows are different for Saturday and Friday, and over the whole year and with the season, that's itself a hard problem, but I won't go into that too much. We use 3 different ontologies of knowledge graphs, and there, you have, let's say,